He's done a lot of amazing work at the intersection of optimization, sampling, differential privacy, robustness, and much more. And he'll be telling us about functional stochastic localization.
Cool, yeah. Thanks so much for having me, and thanks for coming to my talk. So yeah, this talk will be on sort of a new framework that I invented with my wonderful collaborators, my PhD student Anming Gu at UT Austin, and Bobby Shi, who just joined the Simons Institute as a postdoc. Yeah, so this is going to feature a object called the log-Laplace transform very heavily, and I hope that after this talk you will also be very enthusiastic about this object. Okay, so just to give you a sense of how this talk is going to go, it's going to kind of proceed in three sort of independent parts. The first part, sort of my entire goal is just to convince you that the problem I'm going to define is an interesting one and sort of set up the puzzle for the second part of the talk. And then the second part of the talk, I'm going to introduce this new process called functional stochastic localization. And then in the third part, I'm going to give you some actual implementations of this framework, but also some open questions for you to think about. Okay, great. Okay, so this talk is sort of broadly motivated by this, this tool / philosophy that's appeared frequently in the sampling literature called measure decomposition. And the rough philosophy behind this idea is, say you have some complicated measure that you want to understand, maybe you want to prove something about it, maybe you want to sample from it. The idea is that you want to decompose this complicated measure into a mixture of much simpler measures that you actually do understand quite well, right? And I'm going to index sort of this, the component by psi, which you can think of as some sort of exogenous randomness that tells you how I'm going to decompose it, right? And the key sort of property we want this decomposition to have is that we want to say that on average over these components, you actually do recover the original measure, right? So in other words, pointwise over x, if you average over this decomposition, you just get back the original measure, right? And the sort of high-level philosophy for using this strategy is if you want to show something about this, this original distribution pi, then it suffices to sort of show it on average for these components pi psi, and then sort of lift it back using this martingale property back to pi. Okay, so this is sort of like the high-level idea of how to use this strategy. Okay, so a particularly nice instantiation of this strategy was discovered by Eldan. It's called stochastic localization. And in this setting, we're going to insist that our components have a particularly nice form, okay? So the way I'm going to write this form is using this sort of shorthand notation. But let me just digest this for you, because this is maybe not everyone is familiar with this notation. So the idea is that in stochastic localization, I'm going to insist that each component always looks as follows. I always take my original density pi, I downweight it by a Gaussian, and then I tilt it in the direction of psi, right, by a log linear function. I'm going to denote this linear tilt operator by t sub psi, and intuitively you should think that sort of like it favors points pointing in the direction of psi, right? So why is this good? Okay, first because Gaussians are great, right? Like we actually do understand many things about Gaussians that we don't understand about arbitrary measures. So if you want to prove something about pi, and you can actually show this for these sort of Gaussian tilted measures, then you can sort of lift it back to pi, right? And these Gaussian components have all sorts of nice properties. They have nice concentration to measure. We know how to mix Markov chains very fast on them, and so on. Right? Okay. Also, the way stochastic localization is normally framed, you don't have to weight down by just a single Gaussian. You can actually index by a time parameter t and take t to be some very large number. Right, and the intuition is that the more Gaussian weight I'm adding into my measure, the better it is for this overall strategy, right? Because then the Gaussian is even more dominant. Right. Okay, but okay, so I've hopefully convinced you that this is sort of like an interesting strategy where you take pi and you decompose it into these nice components that always have this large Gaussian component, right? And this sort of strategy has been very prolific in the recent literature. It's been used in many applications, including things like convex geometry, proving the chaos conjecture up to polylog in a long series of works. And also, this sort of strategy has been used algorithmically to design faster sampling algorithms by actually going in and using the fast samplers for these components. Right, so it's been a very successful application. But I sort of haven't answered the key question, like why does this decomposition exist at all? Right, and the first part of the talk is just going to hopefully convince you that with a short enough proof that you can leave knowing how to construct decompositions like this. So the key puzzle is I've set up this framework. I want to take pi, and I want to decompose it into these little components. Right? How do you choose a distribution over psi such that this equality actually holds? Right? Like why does there even exist such a decomposition like this? Right? Okay. So I'm going to give you two sort of proofs that are in the literature for this construction. The first one, honestly, like, it's just to make the connection to diffusion models and sort of like give the high-level history for like how this came in the first place. The second one is the one I really want you to leave with like. Hopefully, if I do a good job, you should just be able to memorize that proof. It's simple enough that. Okay. But this is the way that this distribution over psi was originally created when it was first proposed, right? So Eldan wrote down this magical-looking STE and says, if you just run this STE up to time t, take whatever psi t that spits out, and use that to index this expectation. Then this is correct. This is actually a measure decomposition. Okay? And what is this STE doing? It's basically taking your current tilt and pushing it in the direction of the current posterior mean. Okay, so you see the change in psi, which is the current tilt, is a little bit of random noise, but then it's pointing you in the direction of the current mean of your currently reweighted measure, right? So you should think this is sort of some sort of rich get richer phenomenon in terms of the mean, where as the process goes on, the tilt gets localized into a single point because it keeps on trying to decide to move towards the posterior mean. And on average, this will concentrate into a single point. And this is sort of this localization phenomenon, right? OK, so what is the connection to diffusion models? Montanari noticed in 2023 that up to a time change and rescaling, this process is actually exactly equivalent to the dynamics of DDPMs. And this connection has actually been used analytically to get faster analyses for diffusion models. OK, so this is the last time diffusion models are going to show up in this talk. But I just wanted to make sure that this connection was clear for the interested audience. Yeah, question? Yeah, right. So MS is the posterior mean, right? So you look at the current tilted distribution. So use your current psi to create this tilted distribution, right? M is just the average of that distribution. So it's sort of like whatever your current mean is, let me push the entire distribution towards it a little bit. Does that make sense? Yeah. OK. OK, so from here onwards, there will be no diffusion. And in fact, there will not even be any stochastic calculus for the rest of the talk. So it's going to be pretty simple stuff from now on. OK. So let me give you an alternative proof that this distribution actually exists. And this is my favorite proof of stochastic localization, by the way. OK. So it's sort of a more general strategy. Imagine you have a joint measure over two variables, and it happens to be that the x marginal is some target that you really care about, pi, right? And let me define these decomposition components pi psi to simply be the conditional distribution. So in other words, I draw x and psi jointly, and then I cover up x. I only show you psi, right? What is your conditional belief on what x is? That is going to be my decomposition component, OK? And I presented this super abstractly. But no matter how I set up this joint measure, it's always true that this is a valid measure decomposition. And the point is, this is true just by iterating expectations, right? If you average over the conditional measure, you just get back the original measure, right? So the only thing missing from making all of this a valid construction of stochastic localization is just to make sure that my conditional measure actually looks like a tilted Gaussian distribution. Right? Like if I'm able to make this connection, then I've accomplished my dream. I've actually set up stochastic localization, right? So now you just have to be very smart and guess that you should take rho according to the following measure. OK, this will be made much less mysterious shortly. But let me just digest this in the Gaussian case, right? So the joint measure is as follows. I first sample x from your target marginal. And then I sample psi from a Gaussian centered at x. That is my joint measure, right? But you can check that both of these properties hold, right? So like the x marginal is in fact pi, because no matter where x is, this has the same normalizing constant, right? Second, you can check that the conditional law of x given psi actually does look like this, right? So like if you fix psi, the psi squared term disappears, and everything else exactly looks like this. Does that make sense? Yeah, right. So this beautiful proof was due to Ahmed and Andrea Montanari. And it's based on sort of this posterior sampling view of a stochastic localization, where you can equivalently view this distribution psi as coming as follows. You first have a hidden seed draw x0 from the base measure, right? And then you draw psi from its marginal. How do you do this? You draw it from a Gaussian center at x0, and then you throw x0 away. Now I have a psi from the joint measure, the psi marginal of the joint measure. And now each component is just posterior sampling. I show you that psi. What did you think x was?
So Just a remark.
Yeah.
This is very old. This is from the Russian literature.
Cool. It's at least this old. Good.
We just rephrased it in more modern language.
Good. Yeah. Russians figured a lot of stuff out. Okay. So just to complete this story, what happens when I take a time parameter that is more than 1, right? Like I want to index you with a very heavy Gaussian weight, right? Well, no worries. You just have to pick the right joint measure, and the joint measure just happens to look like this, right? Like if you want a linear tilt of psi, then you better cancel out this t, right? And now if you actually look at the psi marginal of this joint measure, you can tell that what happened compared to the previous slide is just that the variance went down by a factor of 1 over t. Right? It's the exact same situation, but with much better variance. And now, when I take t to infinity, this posterior law will just concentrate around x0. Right? It'll be exactly a point mass at x0 in the limit. So this sort of like has a very like pretty mental picture of why this is localization. Right? As you take t to infinity, you're more and more sure about what the original C draw was. Okay. So this is 2 constructions of stochastic localization. Let me make a very brief plug that in the course of doing this project, we found many other sort of like interpretations of this wonderful process in the literature and tried to compile it into a survey. If you're curious, you can check out this survey. This is joint with Bobby and Matzing. OK, so with all of that out of the way, let me first introduce the actual question that we're studying in this paper. The question is, so we figured out how to create a distribution over psi such that this equality holds on average over psi, right? But the key question is, why did I choose a Gaussian here? Like, why did I not choose some other sort of global reweighting to use in each of these components, right? So, well, here's a few answers of why you might want a Gaussian. It's very analytically nice, right? There's a lot of like stochastic calculus tools that are sort of like specialized to Gaussians, and a lot of sort of canonical formulations of problems are sort of Euclidean geometries encoded in the problem, right? Like, maybe you think your function is well conditioned. I mean, that's sort of tied very closely to the Euclidean geometry, right? So the starting question in this paper is, what if I did not insist that sort of every component was weighed down by a Gaussian? What if I instead insisted that I have this like function psi, and I want every single component to be weighed down by the same function psi? Okay, can I make this work? Right. And before telling you whether or not this is solvable, let me just motivate this from the perspective of the optimization literature, which we, as samplers, often like look to for inspiration for primitives. Right. So in optimization, you often, and sampling as well, like not all problems are inherently Euclidean. Right. You might have some constraint set that is more naturally measured by an LP norm or some other norm. And more generally, your pi might have some like local geometry that is changing. Right. Like it might not be like constant curvature everywhere. Right. And following on these sorts of observations of structured optimization, there's been a lot of like really nice success stories in functional optimization. And this includes primitives like mirror descent, where you regularize with an arbitrary function rather than a quadratic. Things like relatively smooth opt, where your notion of regularity is captured by a function rather than a eigenvalues. And interior point methods, where like the entire point is you want to use some sort of local geometry, maybe given by a self-concordant barrier, to guide your iterates and do something different depending on where you are in space. Right, so this has been like a huge success story in optimization. Can we get this for sampling? Okay. So for the rest of the talk, the only thing you need to take away from this first part is this is the key puzzle we're trying to solve. Right? How do we choose a distribution over psi to ensure that this equality holds? And moreover, what functions psi, the regularizer, actually admit a tractable solution to this problem? Right. So this is what I'm going to try to convince you of in the next part. Okay. Let me tell you about some approaches we tried maybe 2 years ago before we understood this stuff better. So the first thing you might try to do is just like take one of the constructions of Euclidean stochastic localization and try to like mash a function in somehow. Right. So if you recall my first construction of Euclidean stochastic localization, you just write a STE that magically pops out this psi. Right. So we tried this for quite some time, and we kept running into some basic challenges. So the first challenge is sort of not too crazy. It's just that if you don't choose to reweight the Brownian motion by some non-local curvature, you're always going to get a quadratic out. So this is sort of like already known in the literature. If you don't change the reweighting locally, you're always going to get quadratics. So you have to use something smart. But sort of like the broader challenge we were running into is a lot of the tools to analyze and design these sorts of localization approaches are really fundamentally Euclidean. Like this is more like of a vague complaint, but like a lot of these things like heat flow, Brownian motion, even differentiating in time at all, sort of felt very fundamentally Euclidean, and we couldn't get this to work. Okay. But now let's go back to the second approach I gave you earlier, which had nothing to do with stochastic calculus, right? It just set up a joint measure and tried to do something, right? Posterior sampling. So here, this felt a little bit more promising, but the challenge that we kept running into was, before I mentioned this thing where you can take t and send it off to infinity, right? And the posterior sampling viewpoint of this is you sort of like convolve infinitesimally up to time t, right? Like you just keep on adding a Gaussian t times. And the trouble is anytime you try to set up these infinitesimal convolutions, you have to dodge these like central limit theorems, right? Like if you don't do things carefully, what will pop out will always be a Gaussian, right? So again, this is sort of like vague, but this is something to keep in mind when I actually do explain our solution. Okay. So in summary, maybe some of the tools from Euclidean stochastic localization will work, but you have to be careful because otherwise you'll run into these issues. Okay.
Do you care that it forms a semigroup?
It will form. The thing we end up producing does form a Markov semigroup. Yeah.
So can I ask?
Yeah.
You seem to be interested in changing the function c, but you're not talking about the linear tilt.
Yeah. So let's say we're committed to using a linear tilt for now, and I just want to change the regularizer. Right? It's kind of like the. Okay, so I'm always coming from like the mirror descent point of view, and in mirror descent, right, like the operator that you're giving is like still linear function plus regularizer, right? So like this is sort of the analog, right? Okay, so now let me tell you about what we did do, and it's going to sort of motivate this object called the LLT, right? So let's just try to solve this problem in the warm-up case where t equals 1. So let's not even think about time, okay? I just want one multiple of psi to like weigh down my function, right? And let me just guess that the law of psi will be given by some measure mu, okay? And just like set up what this would even look like. So I'm just rewriting the above thing for a guess of the measure mu. Does it make sense? So like I'm drawing psi according to this mu, and I'm just like literally writing down what is this evaluated at x, right? But now like if you just rearrange this a little bit, you'll notice that the pi of x cancels, right? This is pointwise true on the left and right-hand side. So what pops out has to be of this form. Okay, like the only psi that you could ever get a solution from this for must look like this. Okay, so like this is some very complicated thing, but it's actually not so complicated because you'll notice what's on the inside is simply the Laplace transform of some measure nu, right? So what this is telling you is that the only psi you could ever hope to solve this problem for must look like a log Laplace transform. Okay, so for this paper, it's kind of like helpful to introduce some notation that we invented called phi sharp, where we're going to parameterize this nu by e to the minus phi instead. Okay, so we're going to work in log space. And the reason I like this, this sort of setting is because there's a really nice analogy between the LLT defined this way, the log Laplace transform defined this way, and a very familiar transform in convex analysis called the Fenchel-Legendre transform, right? You'll notice like sort of the only difference between this and this is taking a pointwise maximum over psi, and this is sort of taking some sort of average over psi. Right? So you can think this is like a softmax version of the exact supremum. Right? Also, like I should mention that this is sort of like, this definition is very central to mirror descent, which is the thing we were patterning off in the first place. Right? Okay, good. So yeah, let me now tell you our solution. So remember, the problem we're trying to solve is just pick a distribution over psi such that this equality holds, right? And I've already committed that my psi will look like a log Laplace transform of something, right? Because this is the only sensible thing, right? Okay, so let me just go back to an older slide and say all you need to do is pick a magical joint density such that the following works. Okay, so we're going to always take psi to be from the psi marginal of some joint density. And we're just going to index the components by the conditional distributions, right? Oh, sorry, this is meant to be like a, okay, and I'll just spoil it. Okay, so the only question left is you need to pick a joint density such that everything magically works out, right? You need this joint density to have two properties. Its x marginal had better be pi, and each conditional law had better look like this, right? If you can pick a pi that happens to have both of those properties, you're done. Okay, so we picked this one. Let's just play with it. So let's see what happens. I first claim that the x marginal of this joint law is exactly pi. Why? Because at any x, if you integrate this quantity, you get 1. Like, in fact, psi is defined so that this cancels out in the normalization, right? So at every x, this is going to be a unit, and therefore it collapses back to pi. OK, great. And then let's just check the conditional laws, right? The posterior laws. So if I show you some psi, what do you think x is distributed as? Well, this goes away. So what are you left with? A linear tilt of e to the minus psi times pi. That's exactly the component that I wanted. Right? So everything magically works. OK, like we actually stumbled upon this like 3 years ago, and we didn't really understand like any of this stuff at the time. But yeah, it turns out that when you're trying to design proximal sort of samplers, which I'll get into later, and you want linear tilts, there's not too many things you can even try. So it's sort of like this entire work is sort of a reinterpretation and sort of process building on top of something we discovered like 3 years ago, but didn't really understand at the time. OK, so let me take a brief interlude to just like wax poetic about this like wonderful object called the LLT. OK, so what is the LLT? So as I mentioned, it's a log of a Laplace transform. And the Laplace transform you can kind of think of as a multivariate MGF, right, moment generating function. And OK, so why do we call it a moment generating function? I think it's because when you take derivatives of it, you get moments. Right, so like I don't actually know if this is true, but right, like
Yes, it is true.
it's true. Good. Yeah. Okay. Good. This is why you call it a moment generating function. It generates moments. Good. And similarly, you might ask, what happens when you take derivatives of this function? You get what are called cumulants. Okay. So cumulants are sort of like moments. In fact, they're just linear combinations of moments. But they're like a little bit different. You'll notice that even in the second cumulant, you already have some sort of centering going on, right? So it's not like literally psi tensor 2. It's like a centered version, right? So it turns out that the first 3 cumulants look like this. You know, it's the mean and then the next 2 centered moments. Starting from the 4th one, they start getting hairy, but I've never used the 4th or higher ever in a paper, so I don't even know what it looks like. OK, here's another fun fact about the LLT. So one very useful property in designing mirror descent algorithms to capture like normed geometries is the fact that if you have a function that is strongly convex in some norm, and you take its Legendre-Fenchel transform, it is smooth in the dual norm, and vice versa. So sort of like these things play very well with norm-based geometry, right? Fun fact, yeah, like this exact same thing is true for the log-Laplace transform. So namely, if phi is strongly convex in some norm, its LLT will be smooth in the dual norm, and vice versa. If you haven't seen these proofs before, they're like extremely short. Like I think, yeah, each one is like OK. So like one of the directions is just Braskamp-Lieb, and the other direction is just Kramer-Rao. So it's quite nice. Yeah, there's some other like nice facts that maybe you can use in your life. This function is always real analytic. It is self-concordant whenever the function phi is convex. These are just things that further this analogy to interior point methods. OK, good stuff. But the main fact that I'm going to need for the rest of the talk is the following fact. So suppose you have 2 potentials indexing 2 distributions. And let me just decide to convolve those 2 distributions, right? So like, let me take mu1, convolve mu2, and say its potential is phi. Does anyone know how the LLTs of like phi1 and phi2 relate to the LLT of phi, by any chance? It's the sum, right? So we know that for Laplace and Fourier transforms, convolution in the frequency domain yields products in the spatial domain. Well, we just took a log, so log of product is a sum. Right? So the point is, if you take the same distribution and convolve it with itself, the LLT is just like multiplying by that number. Right? OK, great. So now I can finally give you the actual construction of FSL. Suppose that you have some psi, and let me just commit to it being an LLT. And let me also commit to the time parameter being a positive integer. OK, so you can't like have like 9.5 here. OK, it has to be like a positive integer. Here's the construction. Again, I'm just going to set up a joint measure that magically collapses into this setting. The joint measure will look like this. OK, so it's exactly what I did before, but I've replaced psi with tau times psi, and I've replaced phi with the tau-fold convolution of e to the minus phi. Right? In other words, you take this measure and you just convolve it with itself tau times. Right? This makes sense because tau is an integer. Right? The claim is that yeah, this is the LLT of this, And that was exactly the previous slide, right? By LLT convolution, this actually is a correct joint measure. So this is really just a special case of the previous slide, right? One kind of cool fact we discovered while completing this project is in some sense, the approach is complete if you insist on linear tilts, right? First, we mentioned as earlier that the regularizer psi, it has to be an LLT, right? Like your hands are tied. You have to have this form, right? Second, we claim that this tau parameter, it actually has to be an integer. Namely, there's some counterexample that we have in the paper that is an LLT, but if you take any multiple of it that is not an integer, it is provably not an LLT anymore. So in other words, if you want to do this process, you have to commit to using integer powers of the LLT. Yeah. OK, so this is the general process, FSL. Okay. Any questions here?
So isn't there a CLT now? Like you just keep convolving. And
but I'm only doing it tau times. I'm not infinitesimal convolution, right? I'm only doing this convolution exactly tau times.
But if I let tau to go to infinity.
Right. So in the limit, you will run into, but for all the algorithmic applications, I'm going to pick a specific tau and stick to it. Yeah. Good question.
Maybe along that question, there are distributions that are stable under convolution.
Correct. Yeah. So we also tried that a little bit. We didn't get very far down that approach, but I think it's potentially promising.
Okay.
You're saying these stable fractional heat flow. Yeah. Exactly. Yeah. We tried that a little bit. We couldn't get it to work, but I think Krishna's had more success with this or some folks. So. Definitely a reasonable.
Could you characterize saying if you want T to be any positive real, it has to be infinitely divisible or something like that?
Yeah, I think probably there are some statements of the problem that make this completeness statement more true, but I guess we just stopped here. Yeah. Okay, cool. So that's the process, but how do you use it algorithmically, right? So first of all, I haven't even defined a Markov chain. So let me tell you the standard way of pulling a Markov chain out of this strategy. So it's Gibbs sampling, right? So if you have a joint measure and you want to sample from its x marginal, a very reasonable strategy called Gibbs sampling is you just alternate between the marginals, right? So from a point x, one step of the Markov chain is to redraw psi from its conditional measure, freeze that psi, and then redraw x from its conditional measure. Right? If you do this back and forth, you can check that the stationary measure is pi. And the question is, how quickly does this actually converge to pi? Right. Okay. Let me first say a little bit about what implementing this algorithm actually looks like for a particular setting. So let's stick to the psi as a quadratic setting for now. Typically, this step, going from x to psi, is viewed as sort of the simple part. It's the forward step, right? And you can think of this as some sort of noisy observation process, right? In the Gaussian case, you're literally just taking your x and drawing a Gaussian around it, right? The backward step is typically the challenging one. This is sort of so we called it way back in the day the restricted Gaussian oracle. It's sort of an analog of a proximal oracle from optimization. But it's exactly taking pi, weighing it down by this quadratic factor, and asking to sample from this overall distribution with respect to x, right? I like to think of this as just posterior sampling, right? In other words, I showed you some psi from the joint distribution, sample from x, given that psi, right? That's exactly what this step is doing. Right? Okay. So what does this look like for a general instance of functional stochastic localization? The forward step is, to sample from this distribution, right? Fix x, draw from the psi marginal. And how do you implement this? Well, as long as you're able to sample from this exponential family, you literally just add up tau copies of it, right? That's exactly the definition of this convolution, right? Okay, so as long in other words, if you believe the tau equals 1 case is simple, you can also implement the general tau case. Just do it tau times, right? And yeah, I kind of like this picture because it really again captures this localization phenomenon for me. If I take some x, I freeze it, and then I show you tau copies of draws from this distribution, you can pinpoint down who x is as I take tau to infinity. Right? The more I take samples from this tilted distribution, the more sure you are about x. Right? And formally, you can just show that the mean is invertible, and you can just recover who x is. Right? Okay. So the fun thing is going to be the backward step. And this is sort of still work in progress, except in some very special cases which we covered in the paper. But again, sort of like the challenge here is to implement this posterior sampling step. And here you have to kind of like get your hands dirty and design some custom samplers. Even in the Gaussian case, many people in this room included have like come up with custom implementations under some structure on pi, right? Like maybe it's Lipschitz or well-conditioned, things like that. Right? Okay, so that's how to implement the oracles. But assuming you can actually implement the oracles, how fast is the overall chain mix, right? Okay, so this I think is a kind of cool specialization of a broader family of techniques to Gibbs kernels. So we're going to write the Gibbs transition kernel as a composition of the forward and backward steps. And you can show that formally these are adjoints. Okay, so like the forward step is the adjoint of the backward step. And how does this like halfway operator k work? It basically takes, so okay, like let's interpret this together. F is going to be a function on psi, right? Sort of like this dual space. And kf is going to be a function on x, right? So like this is going to flip a density from on x to a density on psi, and this is going to flip that density back to x, right? So how does this operator actually work on a function? It just takes the posterior mean, right? So if I apply k and apply it to a function f, like what you will get is just the expectation of f of psi when I show you that particular x, right? Okay, there's this like really beautiful work by Tian and Eldan that shows how to derive mixing times for various like structured samplers, including this one. And specialized to Gibbs samplers, basically what that paper shows is if you can show that the variance goes down every time you do one of these flips, one of these halfway flips, you get a mixing time. So in other words, if every time I flip from f to kf, the relative variance goes down by a factor of 1 plus lambda, then you can show that this implies a Poincare constant of 1 over lambda, and then it'll mix quickly. Right? Okay, so like I basically just reduced to showing this inequality, and the main result of our paper from a mixing time perspective is just that lambda equals alpha over tau suffices. What is alpha? Okay, so tau is just like the time parameter, right? It's like how long do I run this for? The only other parameter is alpha. And you can think of alpha as sort of like a relative strong convexity parameter. So this result definitely holds if pi is bigger than alpha psi in a convexity perspective. You can think this is sort of like the functional analog of strong convexity. Like, are you bigger than a quadratic, right? But in fact, we actually show a slightly weaker condition suffices for this main result, which is called like psi pi. Like it's a functional Poincare inequality, right? Where normally in Poincare inequality you have some like maybe square of the field. Here it's sort of locally weighted by some function, right? And it turns out that this property implies this property. So this is sort of like the minimal condition under which the proof works. Okay. Yeah, so the proof is like a little bit tedious, but in one slide, the idea is to apply the law of total variance and then use those magical cumulant identities I said before. Like as you notice, this is a cumulant this is a derivative of psi, so it is a cumulant. And then you have to do like one key Cauchy-Schwarz somewhere along the way. Okay. Yeah, that's all I want to say about this proof. But one nice thing about this proof is that it actually it's sort of like a new proof even in the Euclidean case, and it recovers exactly the Euclidean mixing results up to the constant factor. So it's like exactly recovers previous things without using any stochastic calculus. So that was something we were pretty happy with. Okay, so with the time I have left, I just want to tell you a little bit about what's happened since this paper. Oh, actually, let me first do one simple example of doing this Oracle implementation. So earlier I mentioned this is sort of like the easy direction. Like for Gaussians, it's literally just like taking your x and adding a Gaussian to it, right? But I want to give you like one example of how to do this for like a phi that is not quadratic, just so that you learn something from this part of the talk. Okay. So here's an example. Suppose you just want to sample from this distribution. The tilts in the x direction of e to the minus phi, where phi is a squared LP norm. Okay, think p is like, I don't know, 4. Okay? Why would you want to do this? This is sort of like a canonical smooth function in LP norms, so you can use this to get some non-Euclidean optimization results. But it's just also like a very instructive puzzle, right? Like, how do you sample from e to the minus LP squared? Actually, just curious, does anyone know how to sample from e to the minus LP squared? Like even just take x equals 0. How would you sample from this over RD? Yeah, it's kind of tricky, and you can imagine things like some tricks that might work for specifically x equals 0 might not generalize to other x, right? Like when x is 0, everything is very symmetric, so you could kind of figure out the sizes of shells, but you can't really do this once I point you in some direction, right? But here's kind of a nice trick that I learned in the course of this project. So here's a univariate fact. If you have e to the minus t squared, you can write this as a mixture of e to the minus t to the p, say for p bigger than 2. And the intuition is, right, you have this thing, maybe it has some heavy tails, like Gaussian tails, and then you want to decompose it as a mixture of super, super light tails, right, like t to the 4. And the trick is you just do this at different scales, right? Like if you can average over the scales, all of a sudden you recover back the heavier tails. It's kind of like an inverse Laplace transform. Okay, so how do you use this to sample? Well, the whole difficulty was that this does not factorize coordinate-wise, right? If it was p to the p, then I'm in business. That's just d one-dimensional problems, right? But here, this is really annoying. But no worries, I'm just going to use this trick and write it as a mixture of psi p to the p. And now, once I've done this, I'm just going to sample lambda from its measure, and the remaining problem is separable. It's a product distribution. Yeah, it's like a stable count distribution. Yeah. Yeah, so it's kind of cute. We're using a measure decomposition within a measure decomposition to actually implement these samplers, which I think is kind of cool. Yeah. Okay, so yeah, just a couple minutes on what's happened since this paper. So as I mentioned, the hard direction is sort of implementing this posterior sampling step. But let me give you some intuition on what this actually looks like. I mean, if we wanted to draw an analogy to optimization, this would be something like you want to minimize a linear function plus some large regularizer plus maybe some fixed measure, right? And notice that interior point methods are kind of solving this problem, right? If you're familiar with interior point methods, like the central path, they're exactly solving this problem where psi is the original objective and tau is something that I decrease slowly to 0, right? So IPMs sort of are exactly solving this problem for changing tau. Now our problem is kind of similar, but we're fixing tau, and we just need to use a sample from this problem for slowly changing psi, right? Every time I do a forward and backwards flip, psi has changed a little bit, right? So we're currently exploring this idea. The sort of high-level takeaway is supposed to be some sort of interior point method for sampling, building on wonderful work by Yunbum and Santosh. This is some work in progress with my students at UT. Okay, another question is the mixing metric. So one reason why we don't or maybe we have other alternatives than chi-squared for tracking mixing times, is because the initial chi-squared divergence is often very big, right? In many applications, it's exponential in the dimension, and this is takes a while to get the burn in, right? But it turns out that also based on some ideas from Yunbum and Santosh, and also way earlier in the literature, you can use an annealing scheme to sort of give yourself a free warm start. So in other words, because this whole sort of framework is very compatible with just adding a multiple of psi, you can just add a huge multiple of psi, sample from that one, and then slowly bring down this temperature. And you can show that sort of this comes for free. Formally, what we can show is that if you're taking at least root d steps anyways, you can kind of get this warm start for free, because the amount of regularization you're adding is making those early stages much faster.
This is an analogy of Gaussian cooling?
Yeah, it's like Gaussian cooling for LLTs rather than Gaussians. Exactly, yeah. Okay, my favorite open question that we are honestly quite stuck on, even with some friendly AI assistance, is when can this mix in KL divergence? And this is sort of connected to some very deep questions in functional analysis, for instance, the lack of an log Sobolev inequality for Hessian reweightings. So yeah, I would love to understand this better. But if you just want to prove some theorem about fast mixing, you can use this free warm start idea. Okay, yeah, that's all I had, and thank you. Yeah, this is a log-Laplace transform. Great.
I don't remember whether Chen and Eldan has done anything for their general framework on entropy.
Yeah, so I mean, they're able to show entropic mixing for like a pretty wide family of these, localization schemes that are quadratic. But like crucially, they're sort of using this like fixed geometry everywhere.
So you cannot adapt their approach.
We tried quite a while. Yeah, in fact, like it seems like there's some numerical counter. Like you can, our previous theorem holds for all convex functions like psi that are LLTs, right? So you might hope that like you can just get entropic mixing always. We have some like numerical counterexamples that seem to say you can't always get this. So really there is some sort of separation between KL and variance. Yeah.
So
Oh. Okay.
Could you use this to prove, like, sort of for specific pies, like try and prove functional inequalities?
Yeah. This is sort of, yeah, right. This is what we're currently thinking about. Yeah.
Okay.
Yeah.
does each one of those measures that in the decomposition, does it have like can you prove any type of concentration about it? So
Yeah.
The main point of that like discussed is that like it has concentration.
Absolutely. So like this is a great question, and this is exactly what we do in this like sort of LP norm application. So this is like why I mentioned this fun fact about strong convexity smoothness duality. So sorry, this is back in my Okay. So like earlier I mentioned that if you pick your phi to be some like smooth function, you can actually get psi to be like strongly convex, right? Okay. In whatever norm you want. And like the point is now in your posterior sampling problem that looks like this or whatever, you got a bunch of curvature and constraints. Yeah. And that's how we got these applications to LP geometry. Yeah. It's on the slide. Yeah.
I guess General Eldan had this general message that if every exponential tilt of your measure has bounded covariance, then you get a point right away.
Yeah.
Is there
I've been thinking about this sentence for a few years at this point, and like it doesn't seem to immediately imply something in our setting, but like, yeah, like exactly this observation that like, what does adding a linear tilt do? It doesn't change the Hessian, right? So like this, it's sort of like saying I have a point covariant inequality for all tilts. It turns out that like when you like map this space like point to point, the Hessian changes somehow, and like this makes things nasty. Yeah.
Thanks. Right, I think we reconvene at 3:30.